Good morning, students. Today we'll discuss how to apply the knowledge of concepts of simple harmonic motion to find the time period and frequencies in certain cases, like simple pendulum, mass attached to the spring, or the U-tube oscillations, liquid in U-tube. So that we will see. So one by one, we'll take all those examples in simple harmonic motion. But first, we'll try to summarize what we have already discussed in our discussions till date. Let me share with you the screen. I hope all of you have gone through the concepts of energy, velocity, acceleration for simple harmonic motion. So we are into the fourth class of module 2, oscillations, in which we are discussing simple harmonic motion. In module 2, we will be learning all these things, but right now we are into simple harmonic motion and other topics will come accordingly. Myself, Dr. Pradeep Sharma from University of Engineering and Management, Jaipur. I always request you to note down my contact number and email ID in case if you want to discuss any problem or doubt. Whatever the topics we have discussed, if you have any doubt or any problem, so you can directly text me up. And in module 2, in oscillations, we will be learning the free vibration, force, and resonance, then mathematical treatment of all these things, and we'll find the resonance and the force vibration and resonance, and then work done against retarding force and sharpness of resonance. All these things we'll discuss, but we are right now into this free vibration part. So that is the introduction of simple harmonic motion that we'll apply over here. The same type of strategy to solve the general equations and other things, and then we'll find the specific conditions in which we will be solving the equations for damped oscillations and forced oscillations. We will try to understand that. So if we summarize, then we can have the definition of SHM. If any object takes such oscillation that it moves back and forth about an mean position under the effect of restoring force, then the restoring force depends on the displacement of the object from mean position, and motion is called simple harmonic motion. So this restoring force is directly proportional to negative of the displacement. F is equal to minus kx, where k is the force constant, and we can have this d2x by dt square plus omega square x is equal to 0 as the differential equation of simple harmonic motion. So this equation we have already solved for its general solution. X is equal to a sine omega t plus phi. So this is the general solution of equation of simple harmonic motion. We can easily find the velocity and the maximum value of the velocity and the minimum value of the velocity. We can find the kinetic energy of this object by using the value of the velocity. We can find the potential energy of this, f dot dx, kx dx, and half kx square, and putting the value of x. This. So as a summary part, if we see, then already we have done all those things, but here just to summarize that what we have done till this point. The total energy is constant, half m omega square by a square, and it represents the total energy of the harmonic oscillator. Average potential energy is for one complete cycle is half k square, and this is the equation when two simple harmonic motions in perpendicular directions they superimpose. So this is general equation of an ellipse now which is inclined to the axis of two-dimensional Cartesian coordinates with the sides 2a and 2b. And when these type of figures are there due to this superimposition, if we have different shapes, these shapes are known as residuous figures. So up to this point, till our last discussion was there. Now we will apply all these concepts to have some examples discussed for simple harmonic motion. We will see how the concept of restoring force and how the concept of displacement in opposite direction to the restoring force we can apply to find the time period of different objects or the frequency. So one by one we will take. So first of all we will take the simple pendulum. All of you know that what a simple pendulum is. So this type of object is a simple pendulum. If there is a string, this is the string, and it is inextensible, massless, and very thin string, and an object of certain mass m is being suspended to it. So this object is of mass m is there, so that weight is working downward, and so you see this as this is going on, you can see here it's an inextensible massless string attached to a fixed point, and the simple pendulum is there. If we apply some force in this direction and release it, it takes the oscillations. Initially the amplitude is large, but later on you see the amplitude goes on decreasing. The decrease of this amplitude due to the friction of the environment and other factors, and later it is taking very small oscillations. But here in this example, the amplitude remained constant. So this is the displacement x and this is the tangent. And the weight is working downwards, but there are two components, mg cos theta and mg sin theta. This mg sin theta is the restoring force, and this mg cos theta is cancelled by this tension. So this tension and mg cos theta factor are cancelled, but the restoring force is actually mg sin theta in this case. So this will consider, and because it is working in opposite direction to the restoring force, so we will consider it as negative. So this will create some acceleration in the system, and we will have m d2x by dt square equal to the restoring force. So m d2x by dt square is equal to minus mg sin theta, And because sine theta is very small, where the number of oscillations are, you can say, sustained. So at that moment when theta is very small, sine theta is equal to theta. So that d2x by dt square is minus g theta. Or we can have d2x by dt square plus g theta is equal to 0, and it is the same type of relation, but here it is x and theta. So we need to change this part. From the diagram, we can easily make out that theta is equal to x by L. So d2x by dt square g by Lx. So we got x and x. Both are here. So now we can make out that omega square is g by L. So omega square is g by L. And if omega is equal to under root g by L, so it is equal to 2 pi by capital T, so that the time period T we can easily find out 2 pi under root L by G. So this is the time period of a simple pendulum in you can say ideal case when there is no damping force available, but you can have a condition that when the oscillations are taking place, the displacement is very small. This angular displacement theta is very small. So this condition needs to be satisfied. So we need to consider that theta is small in this case. So in that case, when this theta is very small, time period is 2 pi under L by G. The second example we can consider for compound pendulum. The compound pendulum is a rigid object, rigid mass, capable of making oscillations, but it can rotate around any fixed axis, passing through any point of its mass, like this. It is not having any definite shape, but it can rotate around any axis passing in between it. So a center of mass is available, so weight will be working downward, and the line joining the axis to the center of mass has distance L, and the angle is theta. So if capital I is the moment of inertia, because moment of inertia will try to rotate it and try to have its position at that particular fixed one. So any axis passing through O perpendicular to its length, then we know that I d2 theta by dt square will be equal to, because this will be the force, the acceleration will be d2 theta by dt square, and the force available will be I. So I d2 theta by dt square will be equal to the restring force mgl sin theta. So we can reduce it d2 theta by dt square plus mgl by I theta. So in that case, we can find that omega square is under root mgl by I is equal to 2 pi by t, so that time period will be 2 pi under root I by mgl. So this is the time period of the compound pendulum. If we know the moment of inertia and other physical quantity of mass and the distance of that center of mass from the axis is known, then we can easily find out the time period. So I hope listeners you can understand this, that it's very easy to find, and whatever the object is, if you know the dimensions and mass and the distance of the axis up to that point where the center of mass is lying, so you can easily find that if that object will take oscillations in simple harmonic motion, what will be its angle. Now the third part is very important as far as the SHM is concerned, mass attached to a spring. Now when mass is attached to a spring, there are different cases. So we will try to explore maximum all. So first case, if we say that okay, this kind of mass is available and the spring is attached to a fixed wall, and we take this oscillation. So restoring force will be F is equal to minus kx and ma is equal to minus kx, like this, because this is the acceleration generated due to this restoring force. So omega square is equal to k by n. So that time period is 2 pi under root n by k. So this is the relation where we need to focus. Time period is equal to 2 pi under root m by k. So this k is the force constant or spring constant of the system that we need to see in different type of arrangements. So this is the first arrangement where a single spring is available and a single mass is available, and it is horizontally moving. Now in second case, if the vertical spring attached to a rigid support, okay, the mass is available here and this type of oscillations are going on. So suppose you see extreme here, extreme here. So in between here, this is the mean position. Okay. So around this mean position, this object is actually taking oscillations. So you can understand this. With the rigid support here, upper one, lower one, and here it's the rigid support. So suppose L is the length of this displacement. So in that case, KL is equal to mg. This is the force, this is the weight supported, so that K is equal to mg by L. Now when body is pulled downward by some distance, so it starts taking oscillations around the mean position, and time period is 2 pi by under root n by k. Now k is the mg by L, so that you can find out capital T is equal to 2 pi under root L by G. So this will be the time period of this type of arrangement. If we are having this information, then easily we can make out. Now the next case is when this type of arrangement is there. There are two springs and a single mass is available to move on a, you can say, a horizontal support. So here the object is connected between two springs of force constant K1 and K2. So there are two springs with K1 and K2, like this. So tensions and force will be available in different manners. So total restoring force will be F1 plus F2 from both the springs. Here F1 is due to first spring, so it is equal to minus K1x. F2 is due to second spring, so F2 is equal to minus K2x. And in result, F is equal to minus K1 plus K2x. So this is this. So it means we can easily find equating this to the acceleration part. T is equal to 2 pi under root m by K1 plus K2. So the result of this type of arrangement, because at any moment both the springs are providing the force to the system. You can understand here. So at any moment the force constant will be sum of these two, K1 plus K2. Now another case when mass m is attached to more than one spring, suppose in here. So this is the first spring of K1 force constant, this is the second spring of K2 force constant, and these two are in vertical direction, mass is attached, but the arrangement is such that these two springs are in series combination. So springs are connected in series. So when in series, the force constant is actually K1 K2 by K1 plus K2. So this is actually 1 by K is equal to 1 by K1 plus 1 by K2. So this is their form. So time period is given by accordingly. So we will put the value of K m by K. So you can find T is equal to 2 pi and the root m K1 plus K2 divided by K1 K2. So this will be the relation for this type of case where two springs are attached in series in vertical direction and the mass is attached. So there is one spring, then again second spring. In the same type of construct when these two are there, but the springs are in parallel. It's not in series, but this type of arrangement is there. So you can understand the first spring, the second spring is available. So the ultimate force constant of this arrangement increases. So ultimate will be K is equal to K1 plus K2. So the time period reduces to T is equal to 2 pi under root m by K1 plus K2. So this way we can identify how this and how we can find the force constant, and if we can get the force constant, then the time period we can easily make out, like T is equal to 2 pi under root mass divided by that spring constant or force constant of that spring. So in this way these can be solved up and we can find the value of time periods. So I hope you understand how we have applied the information of simple harmonic motion to find time period and frequencies of different examples. We will again try to solve a few more examples in the next class. Thank you.